Okay, guys, so what we're going to do is take a look at doing synthetic division. So it is really important that synthetic division is it's a nice way to divide a polynomial, but it only works if you have a linear divisor. So that's going to be the number one thing. So if you're dividing by a linear term, you are good to go for synthetic division. Okay, so the first things first, when we go to synthetically divide, we need to make sure that the polynomial is in standard form. So this is rewritten so that the polynomial is in standard form. The other thing that you want to do is take that divisor and you're actually going to be dividing by the 0. So x minus 1 is equal to 0. And then solve for x, you get x is 1. And so then this is just the format for which we do synthetic division. And all of the coefficients, you'll see the -3, the -2, the 2, and the 1 because they are the coefficients of that polynomial. And then you divide, again, by the 0 of the function. In this case, it's 1. So you always bring down the first term, and then you are going to multiply across, and then you're going to add down. So we've got -3 times, so you multiply by 1, so it's -3. And so you're going to get -3 right here, and then you add down, so that's going to be a -5. And then you multiply by 1, so that's going to be -5. And then you add down, so that's -3. And then you multiply by 1, so it's -3, and then 1 minus 3 is -2. And so this last term is always your remainder. So you take these terms, and now what you're going to do is, remember you started with a cubic function. So this is where you get to fill in all of those other terms. So if you started with cubic, you're now going to have x squared and x, and then a constant. So when you divide by x minus 1, you get -3x squared minus 5x minus 3, and then your remainder is -2, so it's -2 over, and then your divisor was x minus 1. And so this is going to be your answer to that division problem. All right, so let's take a look at number 2. We notice that we put this in descending order, including a placeholder for 0x cubed. And then again, we're dividing by the 0. So we're going to multiply across. So 3 times -2 is -6. Then we're going to add down. So -6 times -2 is 12. Add down, multiply, add down, multiply. So it's going to be positive 58. And then that's going to give us a positive 61. This last term is always your remainder. So we now get to fill in with the terms in descending order. So this is going to be 3x cubed minus 6x squared plus 13x minus 29 plus 61 over x plus 2. Okay, so now we're going to go ahead and notice that this polynomial is already in standard form, but the divisor is 2x minus 1. So the 0 that you had to divide by is going to be 1/2. So again, we list out our coefficients. We're going to multiply. 2 times 1/2 is 1. Add down. 2 times 1/2 is 1. Add down. Half of -12 is -6, and then we've got a remainder of 0. So what this ends up being, again, is you start off with the coefficient and then decrease by one term. So it's going to be x squared plus 2x minus 12, and then I get to box my answer. All right, so now let's take a look at the language here. The following activity is designed to show you what the remainder theorem of algebra states. It says for each of these functions in the table below, use the graphing calculator, so I want you to use Desmos, to determine the given function value. Then use synthetic division to determine the remainder when the function p of x is divided by the given divisor. So what we need to do is we need to look up Desmos, and then we're going to type in Desmos, and then you are going to find the point when x is equal to 1. So if you click on that point, you will find that the y coordinate is -1. And if we want to do that for all three of these, if you type again the polynomial into Desmos, and when x is 2, you get 11. And then when x is -1, you are going to get -1. So make sure that you know how to find that on Desmos. Then we're going to take our divisor, and it's very important that we solve for x. Remember, set each one equal to 0 and solve for x. And then now we're going to do is take our polynomial and then synthetically divide by that process. So I've got 1 times 1 is 1, add down, multiply across, add down, multiply across, add down. Well, if I could multiply across right there, 2 times 1 is 2, and I get -1. So the remainder in synthetic division is -1. Let's go ahead and do this one. This is going to give me 4. That gives me 8. That gives me 7. That is going to give me 14, which gives me 11. So this last term is always your remainder. And then again, I'm going to multiply across, add down. And the last term again is my remainder. And that's what we're doing here. Now I'm going to go to finish this portion off. Again, the function, we wanted you to do Desmos. So if you could do Desmos on all of these, if you were to look up when x is -3 halves, you get 0. And then in this function, when you find the ordered pair, you get 2 and then -11. So again, looking at the divisor, setting each divisor equal to 0, solving for x, and now let's go ahead and synthetically divide. -3 over 2 times 2 is -3. That's going to give me 4. That's going to give me -6, which is going to give me -2. And then that's going to be +3. That gives me -4. Canceling that out, then that's going to give me +6. And then I notice that my remainder is 0. And then let's do this last one here. We've got -3 times 2 is -6. That's giving me -5. That gives me -10. That gives me -11. And so my remainder is -11. So you want to make sure, what do you notice about the 5 previous examples? Well, the remainder of the synthetic division, so if I look at these remainders, it's the same as the y value of the ordered pair that corresponds to this x value, um, which makes that divisor 0. Okay, so if you can replay that if you wanted to. But basically, the remainder of each synthetic division is the same as the y value of the function that corresponds to the x value that makes the divisor equal 0. So let's take a look at the remainder theorem. It says if a polynomial f of x is divided by a factor x minus whatever number, then the remainder must equal f of a. So in other words, if I did p of 2 equals -11, if I were to have divided by the factor x minus 2, the remainder is going to be that -11. All right, so let's take a look at this. This is a little different. It says, for what value of k will this function have a remainder of 8 when divided by the factor of x plus 2? So the first thing we want to do is make sure we do our synthetic division. And so you can take a look at that process right there. So I'm going to have -2 times -2 is going to be 4. And then this is going to give me a 2. This is going to be a -4. So the k minus 4 is just k minus 4. And then k minus 4 times -2 is -2k plus 8. And then if I were to add those down, I'm going to get -2k plus 6 is my remainder. But remember, it's telling us that we want a remainder of 8. So we're going to take our -2k plus 6 and set it equal to 8 because that's what it's telling us that it wants to be. So now we just go ahead and solve for k. And we end up k is equal to -1. So that's the value that k needs to be. All right, so let's try this again with number 2. Again, for what value of k won't make this polynomial have a remainder of 4 when it's divided by x minus 3? So again, we're ready for our synthetic division. We're going to multiply. We get k plus 9 times 3 is 3k plus 27. And then plus 0 is just 3k plus 27 times 3. So that's going to give me 9k plus 81. And then I'm adding these guys together. So I get 9k plus 76. That's my remainder. So I'm going to take that 9k plus 76, and it's saying it wants a remainder of 4. So just go ahead and solve for k. And I get k is equal to -8. All right. So now let's take a look at 3 and 4. Again, you can pause this and try this, and then I'm just going to walk through that step. -1, we get 1. -1, we get -3. We got 3. We got k plus 3. Times -1 is -k minus 3, which gives me -k minus 9. That's our remainder. So we want our remainder to equal 0. So -k minus 9 equals 0. -k equals 9. K equals -9. And so now we found the value of k. So again, we want to just make sure that we are able to synthetically divide. This question is a little different. It says, suppose the function g of x is divided by the factor x minus 2. Which is greater, the value of g of -2 or the remainder when g of x is divided by x minus 2, and it says to show your work. All right, so the first thing I'm going to do is to make sure that I put the proper polynomial in standard form, and then I have my factor x minus 2. I solve for x. I'm synthetically dividing by 2. And so that is going to be -4. I get -1. I get -2. I get 1. I get 2. And then I get a 0. So my remainder in this case is 0. Now I'm going to do g of -2. So there's 2 ways I could do this. I could evaluate by plugging -2 into the function, or I can just literally divide by that -2. It's telling me what x to put. So that's going to give me a 4, which gives me a 7, -14, which gives me -11, and then that is going to be 22. And so I end up, when I evaluate g of -2, I end up getting 20. So it is saying which is greater. So my answer to that is g of negative 2 is greater than the remainder when g of x is divided by x minus 2. So this is my final answer, and the work is my justification. Okay, so let's take a look at the factor theorem. All right, so it's telling you that they give you equations both in factored form, standard form, and a graph. So from the graph, we want to identify the zeros, right? So we're looking at those x-intercepts. So you can see in this first graph, we get negative 2, negative 1, and 1. Then synthetically divide the expanded form of the function by each factor. So this is that expanded form. So I'm dividing by each factor, and then we'll see what we notice. So we've got negative 2, got 0, got negative 1, we got 2, and it gives me a 0. So I always like to box my remainder. So we're going to 1, we got 3, we got 3, we got 2, 2, and 0. And again, I'm just dividing by each of those zeros. So I got 1, I got negative 1, I got negative 2, I got 2, and I got a 0. All right, so notice those remainders are zeros. All right, so now let's take a look at number 2. When we do this, you can use your calculator. I'm just going to go through and work on each one of these. So when I am dividing by negative 2.5, right? So I am going to get negative 1 here. I get negative 1.2, multiply, I get 3, I get 1.2, multiply, I get negative 3, I get negative 0.4, and then I get 1, and then I get 0. If I'm going to do synthetic division with the 0 of 1, then I'm going to get 0.4, which is 0.2, which is 0.2, which is negative 1.6, negative 1.6. That's going to give me a 1.0 times 1 is 1, and then I also get a remainder of 0. So based on what happened in those previous examples, I want you to tell me what the observations you see in the connections between the zeros of a polynomial function, their factors, and synthetic division. So the idea here is that um, when the factors of a polynomial function are set equal to 0 and solved, the results are the x values, called the zeros of the polynomial function. When the polynomial function is synthetically divided by its factors, the remainder is 0. So that brings us to the factor theorem. It says if a polynomial function is divided by one of its factors, then the remainder must be f of a is equal to 0. So this is where you are going to be doing the work and being able to answer these questions. So let's take a look at number 1. The first thing we want to do, it says, is 2x plus 1 a factor of this polynomial? Well, we would need to synthetically divide and see if we get a remainder of 0. Show your work and explain it. What's the graphical interpretation? So let's take a look at our 2x plus 1 equals 0. That's going to give us the fact that x is equal to negative 1/2. So we would have to synthetically divide by negative 1/2. And again, putting all of our terms in descending order. And then bringing down the first term. And then we are going to add and multiply and do all that stuff. And we end up getting a 0. So we know now that 2x plus 1 is a factor of g of x because the remainder is 0. Okay, so since the remainder is 0, okay, so since the remainder is 0, g of negative 1/2 equals 0. So the graph is the graph of g of x is on the x-axis at x is equal to negative 1/2. All right, and so that's what we're going to have you do on number 2, and so forth. All right, so let's take a look. So I want you to make sure that you try that one. And then number 3, it says consider the function and the f of x, and all I did was put a placeholder there. And A says to divide f of x by x minus 3 and then factor the quotient. So when I go ahead and do this, I'm going to bring down the 1. Then I am going to do a different color here. So we're going to multiply. Okay, so the nice thing about that is our remainder is 0, and our quotient is going to be 1x squared plus 3x minus 4, and then we are supposed to factor that. Okay, so in factoring, we will just go ahead and factor that to be x minus 1, x plus 4. So f of x, if I factor everything, I'm not only going to have my x minus 1 and my x plus 4, but I'm also going to have the fact that I divided by x minus 3, and that's the one that started this thing going where I could factor the entire thing. Okay, the x minus 3 was my first one. So let's see what happens when I divide by 1. So I get 1, I get 1, I get negative 12, I get negative 12, I get 0, which means they now have 1x squared plus 1x minus 12. And I'm going to factor that one, and that one's going to be x plus 4x minus 3. So f of x, in this case, I'm going to have x plus 4. I'm going to have x minus 3. And then I'm also going to have the first one I started out with, which was x minus 1. All right, so now I'm going to do this with negative 4 here. So I get negative 4. I get positive 16, I get 3, I get negative 12, I get 0, so I get 1x squared minus 4x plus 3. Factoring that is x minus 3, x minus 1. So f of x in each of these factored forms, x minus 3, x minus 1, and don't forget the first one we started with.